Static systems experience two types of interactions, forces and torques. But now we know we don't call them torques, we call them moments. Forces are actions of one object on another that tend to cause linear motion, while torques, or moments, are actions that tend to cause rotation. We often find ourselves with the need to specify where these forces and torques act. And to do that, we use a position vector. A position vector specifies the location of one point relative to another, and they're always written from one point to another. So if we had a point O and another point A, the position vector that goes between them would look like this, and we would call either OA to denote this is a position vector that goes from O to A, or we could write it, a lot of people like to use an R, with the subscript OA. This is a position vector that goes from O to A. If we wanted to find a position vector based on some known geometry, we typically start with the Cartesian component form because it's the most convenient. So start with Cartesian component form. So let's even go to a 3D example here. If we had, say, an X or a 3D axis here, we could go with X, Y, and Z. And we had 2 points that we're interested in. Maybe one that's in the XY plane here that we call A, and another point floating up here that we call B, which is actually sitting here. The position vector that goes from A to B would look like this. And we can think of the Cartesian components as walking directions. First, we're going to walk in the X direction so far, then we're going to go in the Y direction so far, and lastly, we'll go in the Z direction so far. But keep in mind that it tells you how to get from the starting point to the end point. So in this case, we're moving in the negative X direction, the negative Y direction, and then the positive Z direction. If you're more comfortable with it, we could always write this using the difference in the point's coordinates as something like x2 minus x1 times I hat plus y2 minus y1 times j hat plus z2 minus z1 times k hat. We're going to find that there are two main uses for position vectors here in statics, in the field of statics. Two uses. The first is that we can use a position vector to specify a moment arm. So if you've learned about moments, you know that any point, say point A here, that does not fall on the line of action of a force, like this force F, its line of action runs like this. Point A does not fall on that. A moment is produced by F about A. This position vector R, if we had the geometry, we could use a cross product and find the moment of F about A. The other use is that we can now write forces whose directions we know. So with known directions but unknown magnitudes in vector form. We're going to find this useful for setting up problems later. So when does this happen? Well, if you have a rope, right? We know the force in a rope is going to be along the rope. So maybe there's a rope that runs from point A to point B. So there's some rope running along this distance. We know that the tension in the rope, the force in that rope, is going to act along this line, but we might not know what its magnitude is. Conveniently, what we know is that the unit vector going from A to B, UAB, is the same as the unit vector for the force F, UF. So, in other words, if we know UF, well, we don't know UF, but we could find UAB pretty easy. Then we know UF. How would we find the unit vector of AB? Well, we would start by writing the position vector that goes from AB, right, using geometry, and divide that by its magnitude, sum of the squares, and that would give us a position vector. And in either case, it gives us a unit vector, which allows us ultimately to write that force now as its magnitude, which we may not know, right? So this could be a variable we don't know, times a unit vector that we do know. So one of the processes that you're going to want to get real comfy with, process to get comfy with, is starting with a position vector, turning that into a unit vector, multiplying it by an unknown magnitude to get a force vector. In other words, something like RAB becoming UAB becoming a force vector, which looks like some unknown magnitude multiplied by a known unit vector. And we're going to use this time and time again to solve problems where we know the direction that something acts, but maybe not the magnitude of the force yet.